In this video, we're going to talk about the last topic of Chapter 10, partial pressure. First thing is, let's define partial pressure. Partial pressure means the pressure due to any individual component in the gas mixture. In other words, if you have a sample with multiple gas components, each gas component will make its own contribution to the total pressure. Okay, so that individual contribution is called the partial pressure. And air is a very good example of a gas mixture. We know that air apparently has oxygen, but it's only 21%. And the majority of the gas mixture, the air is actually nitrogen, 78%. And you have argon, carbon dioxide, but the percentage of those gas molecules, gaseous components, quite low. All right, so as we mentioned a moment ago, that the total pressure of a gas mixture equals to the sum of the partial pressure from different gas components. So if you want to use the mathematical equation to express this connection, it will be something like this. P total equals to PA plus PB plus PC, and keep going. Okay, so A, B, C, these are the different gas components. All right, and we know that if those gas components follow ideal gas law, actually you can use ideal gas law to express the P. What do I mean by that? Well, we know that PV equals to nRT. This is ideal gas law. If you divide the V on two sides, that equals to P equals to over nRT over V. All right. What I'm trying to say here is, if you have those different gas components, all of them are following the ideal gas law. So you can actually express the PA by using this equation. In other words, PA equals to NART over V, okay? And PB equals to NB RT over V. PC equals to NCRT over V. You may have a question regarding V. Well, each gas component has its own mole number, that's for sure. But R would be the same as for each gas component, and temperature would be the same because you are talking about the temperature of the whole gas sample, right? Gas mixture. Therefore, for each individual gas component, T would be the same. How about the volume? Well, if you are talking about a gas mixture with a certain volume, that the volume of the gas mixture itself would be the volume of the individual gas components. Okay, so V would also be the same for those gas components. Now let's plug those equations into this equation. That will give us P total equals to NART over V plus NBRT over V plus NCRT over V, and keep going. Okay. Now, as you notice that all of these three parts, they share something common, that is RT over V. So you can extract these parts from all three items. That will give us P total equals to NA plus NB plus NC. Okay, keep going. Times RT over V. Okay. Now, NA, NB, NA plus NB plus NC, add all of the mole numbers together. That is gonna be P total equals to N total, the total mole number of the gas components, times RT over V. Hey, if this equation looks familiar, then you are on the spot, because this one actually tells us that is ideal gas law. In other words, if you have a gas mixture, if all of the gas components are following ideal gas law, then the whole mixture would also follow ideal gas law. That's what it means. Okay, so this is the first equation that we can get from this process. The second equation I want to do here is, we know that P total equals to N total times RT over V. Now, if I do one more thing, PA, let's just use PA, divided by P total, and let's see what will happen. PA, we know that equals to NA times RT over V, right here, okay? And we know P total, based on what we have here, equals to N total times RT over V. And since they are sharing, they're having this RT over V, so they can be cancelled. And so PA over P total equals to NA over N total. Okay, so it looks like the ratio between the partial pressure over over total pressure equals to the mole number of gas component A over the total mole number. Okay, so in chemistry, we define this one as a mole fraction. Okay, and we define that mole fraction as chi mole fraction. Okay, in other words, NA over N total, that is chi. So that tells us PA over P total equals to chi A. Okay, if you are talking about the mole fraction of A, then that would be chi A. Of course, if you're talking about the NB over N total, that's going to be chi B. But if you reorganize this equation, and you will find that the partial pressure of gas component A actually would be the mole fraction of A, chi A, times the P total. Okay, so this is the second equation we can derive based on this process. All right, let's do a quick calculation to demonstrate how we use the equations to do the calculation. Here in this question, it asks a 2-liter gas mixture of helium, hydrogen, argon, and nitrogen has a total pressure of 334 millimeter mercury and at 314 Kelvin. If partial pressure of the 3 gas components individually are here, okay, so, and what is the mass of the argon in this mixture? Well, when you look at this problem, okay, if you want to calculate the mass of the argon, where should we start? Remember the PV equals to nRT. Although mass is not directly involved in this ideal gas law, but if you know the mole number of the argon, then by using the formula weight of argon, you should be able to find out the mass of argon. All right, so our final goal is to find out the mass, but our intermediate goal is to find out the mole number of argon. Okay, so let's write it here so we have a clear target. And we know that since argon is one of the gas components, and we treat this gas mixture as the ideal gas, therefore we can use ideal gas law for argon. That is going to be P argon times V equals to N argon times RT. Okay, so our intermediate target, remember, is N argon. And once we find N argon, we should be able to convert that to mass. So how do we do it? Well, the temperature is known, and R, of course, is a constant, and the P argon is not known. But if you check the equation, the question, total pressure is known, and all the other 3 partial pressures data are given. Remember, from the previous discussion, we know that P total equals to PA plus PB plus PC and keep going, right? So you have P total, and that equals to apparently P hydrogen gas plus P helium plus P argon plus P nitrogen. And you know the partial pressure of hydrogen, helium, and nitrogen, and you know partial pressure, total pressure. So partial pressure of argon should be able to calculate it. So step 2, 334 millimeter mercury, that equals to partial pressure. Let me write it here, okay? So partial pressure of hydrogen plus partial pressure of helium plus partial pressure of argon plus partial pressure of nitrogen, and then that tells us 334 millimeter mercury equals to P hydrogen is 123 millimeter mercury plus helium partial pressure is 32 millimeter mercury plus P argon, which is unknown, and P nitrogen, that is 76 millimeter mercury. All right, so P argon can be calculated. So it would be 334 minus 120 millimeter mercury and 123 millimeter mercury minus 32 millimeter mercury minus 76 millimeter mercury. Okay, so that is 103 millimeter mercury. All right, so the P argon is known. All right, now we can use the ideal gas law now, because P argon, volume, temperature, all three items are known. So let's do the calculation. Of course, remember, when you use ideal gas law, pressure has to be the ATM. So we need to do a unit conversion from millimeter mercury to ATM. And the unit conversion factor is given here. Okay, so step 3, let's convert 103 millimeter mercury to ATM, 7760 millimeter mercury at the bottom, 1 ATM on top. Unit conversion we learned from chapter E. And the V is the 2 liter times 2.00 liter equals to N argon. Okay, I'll write it down here. R is 0.08206 liter ATM over mole Kelvin times temperature 314 Kelvin. Okay, all right. If you do the calculation here, it will tell you that N argon 0.01052 mole. 3 significant figures. I think you can handle the calculation here. Okay, just be careful. All right, now we know the mole number now. Let's convert that to mass. Step 4, 0.01052 mole. Okay, formula weight of argon is given here. So it's going to be 1 mole. Oops. It's going to be 1 mole argon, that is a 39.95 gram. Okay, so final result would be 0.420 gram. Okay, so this is how much the argon, how much the mass for argon. All right, we'll do more practice in class, and if you have questions, let me know.